Hey everybody, welcome back to this TA session. We are now on week 5 or 6 of the dynamics course. Today we're going to be going over 4 different problems from chapter 3. So I'm going to share my screen. All right, so our first problem today is going to be 3/50. And it is about a car going in a circle. All right, so the problem reads, the standard test to determine the maximum lateral acceleration of a car is to drive it around a 200-foot diameter circle. All right, so we got a diameter. Painted on a level asphalt surface. The driver slowly increases the vehicle speed until he is no longer able to keep both wheel pairs straddling the line. If this maximum speed is 35 miles an hour, for a 3,000-pound car, determine its lateral acceleration capability, A sub n, in G's, and compute the magnitude F of the total friction force exerted by the pavement on the car tires. All right, so they gave us the diameter is 200 feet. We're also going to throw the radius right there. So that's 100 feet. They also gave us the maximum speed. So we have a velocity of 35 mph and a mass of 3,000 pounds. And what we are going to be looking for is the acceleration capability, A sub n. Okay, so A sub n equals, and we want that in G's. All right, so if you remember, 1G is equal to 9.8 meters per second squared. But we are going to be dealing with pounds, miles per hour, and feet, so it looks like we're going to need a different unit. You can do the unit conversion, or you can just remember that 1G is also equal to 32.2 feet per second squared. That also means that we're going to want to switch this miles per hour to feet per second. So we can go ahead and do that real quick. We'll just use the unit conversion right now, get it out of the way. Yeah, so thing with that is we are going to have to multiply that by 1 over, so 1 hour over 3,600 seconds. And then also miles to feet is 5280. Yeah, so it's 5280 feet per mile. Cool. Okay. So that is going to give us 51.33 feet per second. All right, so now that we did that, I'm just going to get rid of all of this and drag this over, and we'll just use that the rest of the time. All right, so we have A sub n. That's our first thing we're going to look for. Go back, and Dr. Murray should have given you an equation in your notes, or at least the notes that he sent me. He gave us the equation. A sub n is equal to b squared over the radius of the circle. So So we're going to go ahead and plug in our 51.33 squared. Throw that over our 100-foot radius. And we are going to get 26.35 meters. Wait, no, sorry. Feet per second squared. All right. Yeah. All right. And then in order to get this to G's, we have this little guy over here, little unit conversion. So then the units will cancel out, and G's is not unitless, but it is in a sense. All right. So then we have A sub n equals 26.35 divided by 32.2. Those are both feet per second squared, so those will both cancel. 0.818 G's. All right. Very cool. So that's our first answer. It's the acceleration in terms of G's. And then in terms of normal force, which is what they ask for, the magnitude F of the total friction force exerted by the pavement on the car tires, that is going to be equal to force N. All right, so we have the mass, we have the acceleration here. So all we got to do is multiply them together. So we have 3,000 pounds times 0.818. And then that will give us a force exerted on the tires equal to 24.55 pounds. So even though our mass is in pounds here, you remember that this is unitless, so this will just give us a force of 2,455 pounds. All right, let's go to the next one. All right, and we are just going to move this little puppy over here. All right, so we're going to start with A. Each of the two systems is released from rest. Calculate the velocity V of each 50-pound cylinder after the 40-pound cylinder has dropped 6 feet. The 20-pound cylinder of case A is replaced by a 20-pound force in case B. So actually a couple years ago, I remember doing this one, like being like, what's the difference between like 20 pounds of force because of the mass, as opposed to 20 pounds of just straight force. But it actually matters a lot in terms of acceleration, and you'll see at the end of this that it'll change what we're looking for, the velocity after the 40-pound cylinder has dropped 6 feet. All right, so for case A, you should remember Dr. Mary gave you a formula. It looks like this. U 1 minus 2, this is a work term, equals delta T. And delta T stands for the kinetic energy. So work, if you remember, is the Oh, wait a minute. It is the force times the change in distance from equilibrium. Well, not equilibrium, but from the starting point. So that's U. And then for kinetic energy here, we just have our 1/2 mv squared. Yeah, so all fairly standard. So for this term, you're going to be adding together. We're focusing on A right here. So we're going to keep the left side. As you can tell that the left side is going to go down and the right side is going to go up. Yeah, because it says the 40-pound cylinder has dropped 6 feet. So this one's going to be going downwards. So we're going to add those two together. Oh, it is a hedgehog in my backyard. Man, I haven't seen him in a bit. It's really warm out today, and yeah, I love the warm weather. I'm ready for this. So we're just going to add these two weights together. And then, because this is going to be going up, and we're going to make this downward our positive direction, we're going to subtract that 50-pound force. And then we're going to multiply that all by 6 feet. Yeah, so then that is our U term. And then come over here, this little 1/2 down there. And then we're going to, so this mass right here is going to be the mass for the total system. So we have 40 pounds, 20 pounds, 50 pounds, which in total will be 110 pounds. Throw that over here. And since we want that in mass instead of force, we're going to divide that by our 32.2 feet per second squared, just to get it in terms of pounds. Okay. And then what we're going to do is multiply that by our v squared, which is what we are looking for at this specific moment. All right, so there's going to be 10 times 6, so 60 on this side. We're going to multiply that by 2, get this out of here. And then we have 110 over 32.2. So yeah, we're just going to write it like this for now. It's a little bit janky, but you get the idea. All right. And then we are going to take the square root of this whole thing, so we can get rid of this. And then that is going to be equal to our V. All right, so if you plug this all in your calculator, you should get a value of, well, it's going to be the square root of 35.13 or 5.93 feet per second. Okay, so that is your answer for the velocity after the 40-pound cylinder has dropped 6 feet for case A. All right, so we'll keep that on the screen for now, just so we can compare it at the end. But all right, and then the next part, we are going to, I probably could have stopped that, but we're going to use U 1 minus 2 again equals delta T. This again is the force times, just some of the forces times the change in the distance. And this again is equal to 1/2 mv squared. All right. So for this one, we're going to have the same thing on the left side. So we have, because these are both forces. we have the 40 pounds of force going downwards due to acceleration of gravity, and we have 20 pounds of force just being pushed downwards in general. So we have 40 plus 20, and then again minus the 50, because that is another 50 pounds of force that is resisting this going down due to gravity. And then again multiplied by 6. Okay, so this side is going to be 60 again. Then we get the 1/2 over here. Mass again. This time, this doesn't shouldn't be accounted for in mass. So we have 40 plus 50 divided by 32.2 times v squared. So we have 120 over here times 32.2 divided by, and this time instead of 110 it's going to be 90. All of that in a square root equals v, and then we get a v of 6.55 feet per second. So as you can tell, if you use a force not associated with the actual weight of the system, it's going to accelerate faster. So instead of just waiting for gravity to pull it down all the way, you're just applying 20 pounds worth of force. You're going to see that the velocity after 6 feet will be faster than the velocity after 6 feet in the first case. All right, let's go to the next problem. So the next problem we're going to do is 3/108, and let me just get rid of all of this and pull up that 108. All right, so this one, if you like it, you're going to like the rest of engineering courses in general. I'm a senior right now, so I'm taking a class called Systems, Dynamics, and Controls, and a lot of it has to do with like spring systems, different deflections and stuff like that. So this one should be fun. All right, so we're going to go ahead and read this. The 6-kilogram cylinder is released from rest in the position shown and falls on the spring, which is initially pre-compressed 50 millimeters by a light strap and restraining wires. If the stiffness of the spring is 4 kilonewtons per meter, compute the additional deflection of the spring produced by the falling cylinder before it rebounds. Okay, so we got 6 kilograms coming down, 100 millimeters. This is pre-compressed, which means that we are going to be using, I think I saw in your notes that Dr. Miri gave you, we're going to be using something that looks like this. To account for that. Anyways, we'll just go ahead and write out this whole formula. Kx dx. All right, so that's how we're going to model the spring system once we are looking for the total displacement. All right, so what we are going to start with is we're just going to write down this K value. They give us 4 kilonewtons per meter. We're just going to go ahead and throw that into newtons per meter because they give this to us in kgs, and since it's so light, it's not going to be a big number, and we might as well just work with newtons instead of kilonewtons. So this is 4,000, and it's a very small distance. So we're just going to stick around with millimeters because if you do kilonewtons to millimeters, there's going to be a lot of decimal places. Not decimal places, just a lot of numbers in general. Anyways, 4,000 newtons per meter. All right. So we got that. And we are going to be using the same formula we just did. We got this. The work is going to be done by this weight right here. And that is equal to, so we're just going to start off just doing this. We're not going to worry about the spring for now. So we have work, it's force times distance. This force is going to be mass times the acceleration, which is equal to 6 times 9.81, which is going to give us 58.86 newtons of force, and then we have the distance of 100 millimeters. I'm just going to write down a variable real quick. Which is also equal to 0.1 meters. Then we have this little deflection here. I'm just going to write this down so we keep it there. 50 mm, which is also equal to 0.05 meters. All right, so we got that. And then we're just going to multiply these two little numbers. So we got 58.86 times 0.1. That's just going to move the decimal place over one place. So we have 5.89. Newton times meters gives us, Newton meters, which is the work. All right. So then we're going to set that equal to, so once it comes into contact with the spring, we're going to set that equal to this little ditty over here. All right, so we have this, this initial, this final, negative k x dx. And since this is going to be resisting instead of pushing, there's a note in Dr. Miri's notes that we're just going to keep this positive, so we don't even have to think about it. All right. So we're going to just start throwing in some variables into here. All right. So it starts at, this is the tricky part, because initially I was like, oh, it's like pre-compressed. It still has the same spring constant, like all that kind of stuff. But I chose to keep that in the equation for now, just to see if it mattered later. And it totally does, because when you take the integral, you'll see. Anyways, so we got 0.05 as our initial deflection. And then we have 0.05 plus this final deflection, which is what we're looking for. And then we have 4,000 times x dx. All right, so if you take the integral here, we're going to get something like, we'll do it step by step. So we get 4,000 x squared. And then remember, you divide that, not this part, but you divide that by 2. So we're going to get 2,000 x squared and then from 0.05 to 0.05 plus deflection. Okay, so then we have this 2000. Now we're going to use the top value. And then we're going to throw in 0.05 plus deflection squared. We're going to minus the second term, subtract the second term. Uh, 0.05 squared. All right, so this is the tricky part. It's not really that tricky, but just if you don't pay attention, you might not get this right. All right, so we're gonna have this multiplied, which should be 0.025 0.05 plus 0.1 deflection plus deflection squared. Then you're going to distribute everything. Don't distribute this yet because this is going to end up canceling that. So this is going to get canceled out. That's going to get canceled out. So then you have this 2000 times 0.1. So you're going to have 200 deflection plus 2000 deflection squared. And that's all going to be equal to, because if you remember, we have u1 minus 2. Then this is the kinetic energy. So this is going to be our T equals T. All right. So we're going to set this equal to the U, because this T we just solved for right here in terms of deflection. And then this U, we're just going to throw down here, which is 5.89. Very cool. All right. So now you see this. We're still looking for the final deflection. And if you remember in the last TA session I put on YouTube, we used the quadratic formula to solve for this. Oh, wait a minute. What did I forget? Got something. Oh, that's why. Okay. So I'm just going to fix this now so I don't have to go back in and edit this. But our distance for this guy right here, I shouldn't have multiplied it just by 0.1. I should have multiplied it by 0.1 plus deflection, because that's going to be our final deflection, or like final distance that this travels. So we're just going to be adding another term here. Yeah, so in addition to this 5.89, we're going to have 58.9 deflection. Okay, yikes. All right. Okay. So we'll subtract this from this. We'll just throw a plus 0 over here, so now we're subtracting something. 5.89. Yeah. So this, yeah. So this should be the distance instead. So I kind of want to rewrite that. It's fine. If you don't understand, please shoot me an email. I'll put my email in the description. And I will send you, I have it on my notes right here. It's just, I don't want to rework it right there. Okay. So anyways, now we have 0. So I subtracted this. 0 equals 2. Put this as the leading term. Squared minus, these two will be 141.9. No, 0.1. Yeah, I'm gonna go ahead and just do that. Function minus this 5.89. All right, so now we got this in quadratic form. So now we're just gonna get rid of this messy little work here. Move this up a little bit. All right, so do you guys remember it's negative b plus minus square root b squared minus 4ac over all of that over 2a. So we're gonna have this minus that. Oh yeah, this should be positive. Okay. 141 plus minus squared minus 4a 2000 c negative 5.89. These negatives are going to cancel, so that's just going to make that positive. And then all of that over 2a. Oh boy, that's a good line. So 4,000 on the bottom. This is going to simplify to negative, and this is deflection, by the way. See below that. Negative 141.1 plus minus 117. That's what this is, by the way. Okay, all over 4,000. And that is going to equal 0.029. And these are in meters, by the way, because we're working with meters per second. And then, yeah. And also, comma, negative 0.064. So we know that when this weight goes down, it's going to compress it more, so it can't be a negative number. So it's going to be 0.029 as our answer. Which can also be written in millimeters as 29.4 millimeters. All right, so that is the final answer for this one. Heyo. Okay, and we will move on to the next problem now. Which is 328. Okay, so this one looks pretty fun, right? We got a slider. These could be pistons or something moving around in a machine. So we got sliders A and B are connected by a light rigid bar of length. L equals 20 inches. So instead of just leaving this as 20, make sure that we know that is equal to L. and move with negligible friction in the slots, both of which lie on a horizontal plane. For this position where XA equals 16 inches, all right, so make sure we know that XA at this position is 16 inches. The velocity of A is VA equals 3 feet per second to the right. Determine, all right, so we got a velocity here for A equals 3 feet per second. Yikes. 3 feet per second. Okay. And that since we're working in feet per second, we're going to want to change these eventually, this 20 and this 16 into feet. So just keep that in mind that we have two different units for length going on right now. And determine the acceleration of each slider and the force on the bar at this instant. Okay, so at this instant means we don't really have to worry about these distances changing on us. So they didn't give us B. So let's go ahead and solve for B right there. Let's use their same notation. So for XB be this length right here between, yeah, right about there. All right, so that's XB. So we have 20 as that one, minus 16 squared equals XB. Oh, and if you recognize these two actually make this a 3, 4, 5 triangle. So XB right here is going to be equal to 12. Yeah, so this is going to be the 4 side, 3 side, 5 side. That's pretty cool. So anyways, we already covered a lot of the kinematic equations and how you go from position formula to velocity, and then from velocity to acceleration, and then you go backwards and everything just by taking derivatives and integrals of each one. So like if you have x of b, the velocity can be notated as x dot of b after you take an integral, and then if you go backwards, you can go from the x dot b to x of b. So we have this formula. We can just, I'm just gonna write all the formulas. All right, so we have x squared a plus x squared b equals L squared. So that's our position formula. And then if we go to our velocity formula, we can get x dot a plus x dot b, yeah, equals 0. And that just shows that when the position is changing, the velocity is also changing, just with respect to the different blocks moving in the y and x directions. And then if we take that a step further, we can get the same formula but with acceleration in it. So we'll just write that down here. X double dot a, which is the acceleration, plus, oh boy, that's a bad plus, plus x dot a squared plus x b x double dot b plus x dot b squared all equal to 0. All right, so now that we have this acceleration formula, which is what we're looking for, we want the acceleration of each slider. So we have both accelerations that we are going to look for down here. We have x double dot b, x double dot a. So I think a step that we have to take is we have to look for, we have to like move everything to one side and get one of them by themselves at least. All right, so this is going to become, after a little bit of manipulation, x double dot b is equal to negative x dot squared x a minus x a x double dot a all over x b. And we just got that from moving around these variables. Anyway, and then if we plug in, we can use this velocity we got here, the 3 feet per second. Oh, and since it's a 3, 4, 5 triangle, we can just assume that when this is going 3 this direction, it'll be going 4 this direction, I think. Oh no, I lied. Hold on, I forgot. So we do have enough information to use this. So this is the velocity vector, and they gave us the velocity of A. So we can just plug in and solve for this. So we can rearrange this guy to be solve for the x dot b. That's equal to x a x dot a. We have both of these, and since we have the 3, 4 triangle relationship, we also solve for x b. And then we can just throw in this relationship where we have 16 over 12, negative by the way, and then times xa, which happens to be 3. We get a velocity of negative 4 feet per second. Okay, so then we're gonna use that down here now that we have that. So now we have negative 4 squared minus 3 squared minus xa, which is 16 inches, but over 12. Just converting that to feet for ease. X double dot a. Then xb is 12. So 12 over 12, that's going to be 1. So if we further simplify this, we can get xb, x double dot b is equal to negative 25 minus 4 thirds. I don't want to deal with decimals right now. X double dot a. Cool. All right. So we have this little relationship. I can write that. That is equal to x double dot b. All right. So we're going to save this. Get rid of all this little untidy work here. It's tidy. It's fine. Save this. Throw it up here. So we have it. that anymore. We know that xb is -4 feet per second. Maybe I should have kept that, but okay. So we still have these three guys. So next we are going to be just looking, because now we are looking for, what did I look for? Oh, the force of the bar. All right. So for force of the bar, we're going to use T as like a tension kind of deal. And we're just going to draw a couple free body diagrams. So let's just start with block A. So we have block A right here. So we have mass acceleration, force coming down this way, just due to gravity. We have 10 pounds acting on it this way. And then we have the tension, and we just need the general direction of it, so we can relate them in the end. So we're just going to write a little triangle over here. We'll just give it 3, 4, 5. Just so we don't have to like deal with cosines or sines or anything like that. So then from this, we can just basically make an equation. So we got 10 pounds going this way. We'll use x going this way as the positive direction. So we got 10 minus, looks like the tension is going to be pulling it this way. So 4, 5, do 4/5 of the tension. And then for the y direction, we are going to use, so it's 4 pounds. And we want to switch that to a mass, I think. So we'll divide that by 32.2. And then, so since it's going to be equal to ma, we'll multiply that by the acceleration, which is x double dot a. So now we have a term that relates tension to the acceleration. Yeah, so we have two unknowns here that we can't solve for yet. So let's go ahead and do the free body diagram for XB, or just for block B in general. So now we got block B. I'll label this one A. This is A. That's block B. Yeah, okay. So this is block B. What do we got here? This is normal force on B. That's equal to MA. We got this force, gravitational force down on it. That's just going to be 6 pounds divided by 32.2, just to get that mass. Then acceleration, we want acceleration in the y direction. Yeah, okay. So then for this one, we have tension going this way. And we'll use that same 3, 4, 5 triangle. Okay, so we'll start with the tension side. So for this block, we don't have anything pulling in either direction because it's going straight up and down in the y direction. So we're going to use, and y direction, we're going to keep positive going up, just for the sake of having a sane coordinate system. So we have -3 over 5 t, and then that's going to be equal to this 6 over 32.2 multiplied by the acceleration block. Wait a minute. Yeah. acceleration of block B. Okay, so now we have that. Cool. All right. So now you're going to ask, wow, so now we have three equations, which both have two unknowns. But here we can make another relationship between x double dot A and x double dot B, because we have two same variables split between them. So we could go any which way here. Like we could put xb into this first equation, this negative 25. Okay, we're gonna use this as equation. We'll say this is equation 1, equation 2, equation 3. So basically, I'm gonna use the replacement method. You can go whatever method you want to use. Like you could use matrices, you could do pretty much anything to solve for these variables. I think the replacement method is probably easiest just because you have a bunch of untidy numbers. Like you have the 6 over 32.2. You have a 4/3 here. 4/5 isn't too bad. But yeah, like matrices or like systems of equations generally work better with like whole numbers or something like that. So I'm just gonna use replacement. So basically, so if we clean this up a little bit, we can get we can solve for t. Show that this t is equal to what do I got? Let's put the steps in. Oh, wait a minute. All right, so yeah, from this b equation, we get t equals negative 0.311 x double dot b. All right, and then if we go ahead and throw this, clean this equation up, we can get a I'm just going to plug this t into this. So we get another relationship between x double dot b and x double dot a. So if we do that, we can rearrange and get that. 10 plus 0.248 x double dot b All right, so now we have this relationship, and if we clean this up a little bit, rotate everything around, we can find that x double dot b is equal to 0.124 x double dot a minus 10, all divided by 0.248. I'm skipping a little bit of steps here, but basically this equation right here, just move this 10 over and then divide by 0.248 and you will get this. I also simplified this 4 over 32.2 into 0.124, just so we wouldn't have multiple divisors going on at the same time. So now we have this equation up here. We have x double dot b. So now we have two relationships between x double dot b and x double dot a. So if we set these equal to each other, we'll get 0.5 x double dot a minus 40.32, and then that will be equal to negative 25 minus 4 thirds x double dot a. Then, yeah, so then we'll go ahead, solve this. So then on this side, you're going to get 1.83. We're going to move this 4 thirds x double dot a over this way. Just add it to this 0.5. What am I doing? 83 x double dot a equals, then we're going to add this over here. So we're going to get 14, or no, sorry, 15.32. 15.32. Yep, and then that is, if we just divide by 1.83, we'll get x double dot a, which is the acceleration they asked for. Well, one of the sliders, that's the a slider, as 8.3 feet per second squared. All right, so now we have that. I'm just going to get rid of a little bit of work here. Actually, no, I'm going to keep that one. Let's move it up a little bit. So anyways, if you use this x double dot a, just plug it in over here, and then you can find x double dot b is equal to negative 36.1 feet per second squared. And then you can use either of these, plug them into either of these equations, and just solve for t. But I'm not going to waste your time right now. I'm just going to write t is equal to 11.21 pounds. Yeah, so that is the end of the equation. So these are our answers. We have the force on the bar as 11.21 pounds. We have acceleration of block A as 8.3 feet per second squared. And we have the acceleration of block B as negative 36.1 feet per second squared. Thank you for coming today. Really appreciate it. Have a good one, everybody.